This module covers heat and temperature, and temperature is obviously one of the most important variables when talking about weather, but none of this would even matter if there was no heat, and it's because heat actually drives everything in our atmosphere. So that's what we're going to be talking about this week. This first lecture is going to cover heat transfer, so how heat moves from one location to another and why that happens. The goals for this lecture are to first understand what temperature is. We have misconceptions about that. To know what heat is and how it travels, and then to talk about the different types of heat transfer. So first let's talk about temperature. When you think of temperature, if you're like me, you probably think of it as a definition of how hot or cold something is. But what does it actually mean? Well, to understand that, we need to think about on a molecular level. So think about everything around you right now. The air you're breathing, the chair you're sitting on, the computer in front of you, even your own body is made up of trillions and trillions and trillions of tiny particles called molecules. And interestingly enough, these molecules actually aren't frozen in place. Rather, they're actually moving. And when we talk about temperature, we're simply talking about the average motion of these molecules. Or another way to put it, the speed of the molecules. Now with that said, the warmer an object is, the faster the molecules are moving. The colder the object is, the slower those molecules are moving. And this brings us to an interesting point. When we look at our own Fahrenheit scale, we know that there's negative temperatures. If you've ever been to the Midwest or if you've ever been to northern Canada, you've probably experienced below zero temperatures. Even in the Celsius scale, that's the scale that pretty much everybody else in the world uses, they also have negative temperatures. But how cold can it actually get? Well, if temperature is defined by motion, well, absolute zero would be achieved when there's no molecular motion. And in fact, there's a temperature scale that I'll talk about in a future module that has an absolute zero, and that scale is called Kelvin. So, just to reiterate, when an object has a cold temperature, that means that the molecules in that object that are making up that object are moving very slowly. On the other hand, when an object is really hot, those molecules are moving really fast. Or if you like to look at it in a more lighthearted view, like I like to, when an object is really warm, the molecules are bouncing off of each other, bumping off of each other, going really fast. On the other hand, when the object is cold, the molecules are gliding by slowly and gently. They're bumping into each other, they're bonding, they're hugging and kissing, getting married, having children in a white picket fence house and stuff like that. No, not really, but they move slower. Now, with this said, objects actually have different temperatures. Don't believe me? I'm sure that you've stepped outside before and it's felt really hot. Other times it's felt really cold. Well, every object surrounding you right now has its own unique temperature, which means that those molecules have their own unique speed. And this results in imbalance. One object could have a cold temperature, whereas another object right next to it could have a hot temperature. And heat exists because of this imbalance. So here's what happens. When you have two objects, one warm, one cold, Mother Nature hates imbalance. Mother Nature does not like it. A natural system does not like it when it is imbalanced. As a result, exchange happens. And in this case, heat is energy that's moved from the warm object to the cold object until the two objects have the same temperature. So when we talk about heat, Heat exists because two objects don't have the same temperature, and then heat travels from the warm object to the cold object. Now this right here is very important. This is something I would love for you to remember. From warm object to cold object, until the two have the same temperature. When that happens, the system has reached a state of what's called thermal equilibrium. The two objects have the same temperature, heat transfer stops. And the two objects are just next to each other with the same temperature. Think about if you're like me and you love frozen pizza. You take a pizza out of the fridge. What do? You usually stick it either in a microwave or an oven. Well, when you stick it in an oven, that actually is surrounding it with very hot air. And so now you have really hot air surrounding a cold pizza. Well, since Mother Nature hates imbalance, heat transfers from that hot air to that cold pizza. And heat continues to transfer until one of two things happens. Either the two objects reach the same temperature, so the pizza becomes as hot as the air. In this case, you're going to have a very burnt pizza, depending on how high your oven setting is. Or you take the pizza out of the oven. And then the same is true when you take that hot pizza out, now it's in cooler air. Heat is escaping from the pizza to the surrounding air, which is why the pizza cools down. So just an image of this. If you have two objects, a hot object and a cooler object, heat will transfer from the hot object to the cool object. And then eventually, the two objects are in thermal equilibrium. Heat transfer has stopped. Now, there are two types of heat. And one type we're going to talk about today, and the other type we're going to talk about in a few weeks. So, the type we're going to talk about today is called sensible heat. This is heat that you can actually feel. So, when you put your hand on something and your hand feels cold, that's because heat is actually escaping your hand and going onto the cooler object. You feel that heat transfer. On the other hand, if you touch something hot like a hot pan that you just pulled out of a stove, out of an oven, you're going to feel heat transfer from the pan to your hand, so that feels hot. So that's sensible heat. That's what we're going to be talking about today. Another type of heat that is more hidden is what's called latent heat. To understand latent heat, we have to understand a little bit about phase changes in water. So water exists in three different phases. It could either be gas, which is water vapor, liquid, which is just the liquid water that you pour out of your faucet, and ice, solid water, ice. And water constantly is changing between those phases. And when it does that, it needs to absorb a certain amount of heat to evaporate or to melt, and it needs to release a certain amount of heat in order for it to condense or freeze. And that's what's called latent heat. So in a case such as water evaporating, it absorbs heat. And that's because the water molecules are going faster, they're spreading out, and so heat is absorbed in that case. On the other hand, when water condenses, heat is released. The water molecules are slowing down, they're sticking together, and that results in heat being released. Now, we'll talk more about latent heat in a few weeks, but for now, we're going to stick to sensible heat. Now, there are three ways that sensible heat travels, three types of transfer. And you've probably heard of them before, but if you haven't, here we go. They are conduction, convection, and radiation. So we're going to talk about conduction and convection in depth today. The next video, actually the next two videos, are going to cover radiation more in depth. So without further ado, let's talk about conduction. So do me a favor, and while you're watching this video, put your hand on an object. And you feel that heat, right? Either traveling from the object to your hand, In that case, it would feel hot, or traveling from your hand to the object. In that case, it would feel cold. This is a heat transfer that's through direct contact. You have two solid objects, your hand and then the object you're touching, and heat is traveling directly between the two of them. That is an example of conduction. Now, another example of conduction is, let's say instead of you directly touching that other object, you have some kind of intermediate object, maybe a pole, maybe a piece of paper or something, between you and the other object. Heat is going to transfer from your hand through that intermediate to the other object. That is conduction. Heat transferring through an intermediate object called a conductor. And so that's what conduction is. Heat travels from the warm object through the conductor to the cold object. Think about if you've ever been to a bonfire before. If you're like me, one of your favorite pastimes is roasting marshmallows. Also, if you're like me, you might have something like a skewer or even just a wire hanger. And if you hold that wire hanger into the fire, heat will eventually transfer from the fire through the wire hanger to your hand. And if you're not careful, you can burn your hand. That is an example of conduction. Heat travels from the fire through the hanger to the cold object, which would be your hand. In this case, none of the objects have to move in order for heat to transfer. The fire is not moving, your hand's not moving, the wire hanger is not moving. In this case, nothing is moving. With all of this said, some objects do a really, really good job of transferring heat through them. So, for example, that wire hanger does a really good job allowing heat to pass through it to your hand. But what if instead of a wire hanger, what if instead you had a wooden stick? Wood doesn't do as good of a job. Heat doesn't transfer through wood as easily. That's what's called an insulator. And it's just like the insulation in your house. It prevents heat from the outside coming in or heat from the inside going out. That insulation acts as a poor conductor. It blocks heat from transferring through. Another good poor conductor, another good example of a poor conductor is air. As a matter of fact, let me step back for a second. As a matter of fact, when the atmosphere is heated up, only the very, very, very lowest centimeter or two of the atmosphere is actually heated up by conduction. So something else has to be involved in heating up the atmosphere. Much of what we'll be talking about the rest of this module will cover that something else. So again, here's an example. If you have a fire, like this little candle right here, and you have a stick, and it's a metallic rod, maybe something that you're like gonna poke one of your annoying friends with, or annoying teachers with. No, don't do that. But let's suppose that you did do that, and you're holding it over a flame. Well, heat is going to transfer from the flame through this conductor to your hand. So you don't want to hold it over for too long because otherwise you're going to burn your hand. The next type of heat transfer is much more important in the atmosphere, and that is convection. Convection involves the transfer of heat through movement of a fluid. Now this is different from conduction. Conduction involved solid objects. Convection involves fluid. Interestingly enough, when you think of fluid, you think of water, liquid, something like that. But believe it or not, the atmosphere is a fluid in that things are free-flowing, they're compressible, they take on the shape of a container, just like water does. So the atmosphere is actually a fluid. And so convection occurs in the atmosphere. Another good example of convection is boiling water. If you've ever boiled water before, you see bubbles rising up from the bottom of the pan up to the top. Well, what's happening is that the bottom of the pan gets really hot from the flame or from the electric kettle, and then it heats that water at the bottom up a lot. And then as that water gets hot, those bubbles begin to rise. And so that's how convection works. Basically, you have rising motion that happens here. Heat starts at the surface and then rises. Now, as it's rising, it's not rising into empty space. No, it's actually rising into space that's being occupied by something. In order for it to rise, it has to push that something down. And it pushes that something down, and then that something, which was cooler air in this case, then makes it down to the ground, and it warms up. And then it begins to rise. And it pushes cold air down. And then that cold air warms up, and it begins to rise. That pushes more cold air down. And then that begins to warm up and rise. And this process keeps happening until you have what are called thermals. They're these bubbles of warm rising air. They start at the ground, they get hot, they rise, they force cold air down to take their place, then that cold air gets hot and it rises. It looks something like this. So let's say you have a hot ground and it's heating the air right above it. This is where conduction comes in. That lowest centimeter or two gets really hot. And as it gets hot, it rises. As it's rising, it pushes cool air back down to take its place. That cool air then gets hot, and it rises. And then that forces more cool air down, and then it gets hot, and then it rises. And you get the formation of these rising bubbles of hot air called thermals. And another drawing of it, this one's a little bit cruder, but it still gets the job done. The sun heats the ground up. The ground heats the atmosphere up. It heats that just very lowest layer, which then rises, forcing cool air down, which then heats up and then rises. And you get these constant circulations. And this is actually how our atmosphere heats up. It heats up by the ground heating the air up. Now, these rising motions are actually very essential to recreational hang gliding. If you're a hang glider or if you've ever seen anybody glide before, these rising thermals can provide them with a substantial amount of upward motion. So not only are they important for heating up the atmosphere, they're important for some hobbies too. Now, what happens to this rising air, though? Well, as air rises, it forms these thermals. We actually have another name for them as meteorologists. These isolated bubbles of rising air are also called parcels. Now, what happens to air pressure as you begin to rise in the air? Well, if you remember from Module 1, as you rise up in the atmosphere, there's less and less weight above your head. As a result, air pressure is lower and lower and lower. This causes the air in that bubble to expand. As it expands, it gets cooler and cooler and cooler. Now, at the same time, this bubble acts like an isolated entity. It does not exchange any heat or energy with its outside environment. This is what I like to call the Las Vegas rule. What happens in the parcel stays in the parcel. So as this parcel of air is rising, it's not exchanging any heat with its surroundings. So it's not absorbing any heat, warming up. It's not giving off any heat, cooling down. Instead, it's only changing temperatures due to expansion. So as the air rises, it expands and it cools. Now the opposite is true too. If you have a bubble of air, a parcel of air, higher up, and it begins to sink, it will compress, and that compression causes warming. Now we're going to talk more about this cooling and warming in the future when we talk about what's called adiabatic processes. But for right now, just know that as air rises, it expands and it cools. And as air sinks, it shrinks and it warms. That's enough to get you through right now. We're going to talk more about this process in a few weeks. So let's say you have a parcel of air and you push it up a mountain. As it rises in that mountain, it expands. And as it expands, that expansion causes cooling. Another good way of looking at this, if you've ever used compressed air or if you've ever used hairspray, the hairspray inside that canister is room temperature. But when you spray it onto your hair, it feels cold. Well, it's because all of those air parcels from inside the canister were compressed. When they shoot out, they expand. That expansion causes them to cool. The opposite is true when you have a larger parcel that's forced downhill. As you go downhill, or as a parcel sinks, air pressure increases. That causes the parcel to compress and get smaller and to shrink. This causes warming to happen. And in fact, when contents are under pressure, I'm sure you've seen that label, warning, contents under pressure. That means that there's a good possibility for warmth. And so air can contract and warm as it sinks. There's one other special type of convection I want to talk about. Up to this point, the convection that I've talked about has dealt with vertical motions, air rising and air sinking. But if you've ever been outside on a windy day, you know that air also moves horizontally. And it can bring with it either warm air or cold air. We in the world of meteorology call that advection. And this is a word I'd like you to remember, because advection means the horizontal transfer of heat and cold. So if you've ever been outside on a warm day and then suddenly it got cold, chances are what you experienced was advection. A warm air mass was pushed away and a cold air mass came in and took its place. Advection is really important when talking about heat distribution on Earth. And advection looks something like this. When you have cool air pushing in and warm air pushing away, being pushed away, that's what we call cold air advection. On the other hand, if you have warm air pushing in and cold air being pushed away, we call that warm air advection. So cold air advection happens when cold air pushes in. Warm air advection happens when warm air pushes in. We'll talk more about this in a few weeks when we talk about fronts. But for right now, advection is the horizontal transfer of heat. The last thing I'll talk about for this lecture is radiation. So if you've ever been to a bonfire and you've had your marshmallow and you've roasted it on the wire hanger and you felt the heat, that's conduction. You watch the flames rising up, that's convection. That heat that's rising, that's convection. But you may have also experienced a sensation when you're standing near the fire, but the flames aren't hitting you, but it feels warm. You feel heat coming off the fire. That, my friends, is radiation. What you're actually experiencing is radiation. And when we talk about radiation, people often think about Homer Simpson or Fukushima or nuclear bombs or stuff like that. But believe it or not, radiation is simply another form of heat transfer. And we get most of our radiation from what I like to call the biggest bonfire known to man, the sun. And we're going to talk more about the sun in the next lecture on radiation. So join me then. Until then, I'm Terrence Mullins. Thank you for watching.